National Electrical Code, commonly referred to as the NEC, does not specifically mandate U-shaped cutouts or elongated holes for grounding electrode conductor, also known as GEC, entry points into enclosures. The common practice of routing the grounding electrode conductor through an existing hole or drilling one is widely accepted and considered sufficient for most installations. High current fault currents flowing through a grounding electrode conductor can potentially induce heat in the surrounding enclosure. However, this is generally not a significant concern due to several factors. Firstly, fault currents typically last for a brief period before circuit breakers or fuses trip, minimizing the duration of heat generation. Secondly, grounding electrode conductors are typically sized to have a low resistance, which minimizes the amount of heat generated during a fault. Thirdly, modern enclosures are designed to withstand the heat generated by fault currents without causing damage or creating a hazardous condition. In some cases, additional measures may be necessary to ensure proper grounding and prevent potential heating issues. Firstly, ensure that the grounding electrode conductor fits snugly through the hole to prevent arcing or vibration. Secondly, establish a good metallic bond between the grounding electrode conductor and the enclosure using a grounding lug or bonding strap. Thirdly, provide sufficient space around the grounding electrode conductor entry point to allow for heat dissipation. For further guidance on grounding electrode conductor installation, refer to the National Electrical Code Article 250 and IEEE Standard 142-2023, Grounding of Industrial and Commercial Power Systems. The National Electrical Code Article 250 provides comprehensive requirements for grounding and bonding, including grounding electrode conductor sizing, installation methods, and connection requirements. IEEE Standard 142-2023 offers detailed recommendations for grounding systems in industrial and commercial power systems, covering various aspects such as grounding electrode design, bonding techniques, and surge protection. Grounding electrode conductors play a critical role in electrical safety by providing a low impedance path for fault currents to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers and fuses. Proper installation of grounding electrode conductors is essential to minimize the risk of electrical shock, fire, and equipment damage. The size of the grounding electrode conductor is determined based on the size of the service entrance conductors or the equivalent size for separately derived systems, as specified in NEC Table 250.66. The grounding electrode conductor must be made of copper, aluminum, or copper-clad aluminum and must be protected from physical damage. The grounding electrode conductor must be connected to a grounding electrode system, which can consist of various electrodes such as metal underground water pipe, ground ring, rod and pipe electrodes, and plate electrodes. The connection between the grounding electrode conductor and the grounding electrode must be made using approved methods such as exothermic welding, listed pressure connectors, or bolted connections. When routing the grounding electrode conductor through an enclosure, it is important to maintain the integrity of the enclosure's grounding system. The grounding electrode conductor should be bonded to the enclosure using a grounding bushing or other approved fitting to ensure a low impedance path for fault currents. In situations where the grounding electrode conductor passes through a metallic enclosure, induction heating can occur if the conductor is not properly bonded to the enclosure. Induction heating is caused by the magnetic fields created by the fault current flowing through the conductor, which induces circulating currents in the metallic enclosure. These circulating currents can cause the enclosure to heat up, potentially leading to damage or creating a fire hazard. To minimize the risk of induction heating, the grounding electrode conductor should be bonded to the enclosure at both the entry and exit points. This creates a closed-loop path for the fault current, reducing the magnetic field and minimizing the circulating currents in the enclosure. Alternatively, a non-metallic enclosure can be used to eliminate the possibility of induction heating. When drilling holes for the grounding electrode conductor, it is important to select the appropriate drill bit size and ensure that the hole is clean and free of burrs. A hole that is too small can damage the conductor or create high resistance connection, while a hole that is too large can allow moisture and contaminants to enter the enclosure. Burrs can also create sharp edges that can damage the conductor's insulation or create a path for arcing. The grounding electrode conductor should be installed in a manner that protects it from physical damage and corrosion. The conductor should be supported and secured to prevent it from sagging or rubbing against other objects. The conductor should also be protected from exposure to corrosive environments such as salt water or chemicals. In some cases, it may be necessary to install the grounding electrode conductor in a conduit or other protective raceway. The grounding electrode conductor should be inspected regularly to ensure that it is in good condition and that all connections are tight and secure. Any damaged or corroded conductors or connections should be replaced immediately. In addition to the requirements of the National Electrical Code, local codes and regulations may also apply to grounding electrode conductor installations. It is important to consult with the local authority having jurisdiction to ensure that the installation meets all applicable requirements. Grounding electrode conductors are an essential component of a safe and reliable electrical system. By following the recommendations in the National Electrical Code and IEE Standard 142-2023, and by implementing best practices for installation and maintenance, you can minimize the risk of electrical shock, fire, and equipment damage. When installing a grounding electrode conductor, it's crucial to consider the type of grounding electrode being used. The NEC recognizes several types of grounding electrodes, including metal underground water pipes, concrete encased electrodes, ground rings, and rod and pipe electrodes. Each type of electrode has specific installation requirements that must be followed to ensure effective grounding. For example, metal underground water pipes used as grounding electrodes must have continuous metallic contact with the earth and must be supplemented by an additional electrode. Concrete encased electrodes, also known as UFA grounds, must be encased in at least 2 inches of concrete and must be located within the bottom of a concrete foundation or footing. Ground rings must be buried at least 30 inches below the surface of the earth and must encircle the building or structure. Rod and pipe electrodes must be driven at least 8 feet into the earth and must have at least 8 feet of contact with the soil. The selection of the appropriate grounding electrode depends on several factors, including soil conditions, availability of electrodes, and local code requirements. In areas with high soil resistivity, it may be necessary to use multiple electrodes connected in parallel to achieve a low enough grounding resistance. The grounding electrode conductor must be sized based on the size of the service entrance conductors or the equivalent size for separately derived systems, as specified in NEC Table 250.66. The size of the grounding electrode conductor is determined by the ungrounded conductors. For example, if the service entrance conductors are 4/0 AWG copper, the grounding electrode conductor must be at least 2 AWG copper. The grounding electrode conductor must be continuous from the grounding electrode to the service equipment or separately derived system. Splices are not permitted in the grounding electrode conductor except for reversible compression connectors listed for the purpose. The grounding electrode conductor must be protected from physical damage by enclosing it in conduit or other approved raceway. The grounding electrode conductor must be securely fastened to the surface on which it is carried. The grounding electrode conductor must be installed in a neat and workmanlike manner. When the grounding electrode conductor is run through a metallic enclosure, such as a panel board or junction box, it must be bonded to the enclosure to provide a low impedance path for fault currents. The bonding connection must be made using a listed grounding bushing or other approved fitting. The grounding electrode conductor must be installed so that it is accessible for inspection and testing. The grounding electrode conductor must be identified by marking it with the word ground or the grounding symbol. The grounding electrode conductor must be connected to the grounding busbar in the service equipment or separately derived system. The grounding busbar must be securely fastened to the enclosure and must be made of copper or aluminum. The grounding busbar must be sized in accordance with NEC Table 250.28. The grounding busbar must be connected to the neutral busbar in the service equipment or separately derived system. The connection between the grounding busbar and the neutral busbar must be made using a bonding jumper. The bonding jumper must be sized in accordance with NEC Table 250.102. The bonding jumper must be continuous from the grounding busbar to the neutral busbar. Splices are not permitted in the bonding jumper except for reversible compression connectors listed for the purpose. The bonding jumper must be protected from physical damage by enclosing it in conduit or other approved raceway. The bonding jumper must be securely fastened to the surface on which it is carried. The bonding jumper must be installed in a neat and workmanlike manner. When the bonding jumper is run through a metallic enclosure, such as a panel board or junction box, it must be bonded to the enclosure to provide a low impedance path for fault currents. The bonding connection must be made using a listed grounding bushing or other approved fitting. The bonding jumper must be installed so that it is accessible for inspection and testing. The bonding jumper must be identified by marking it with the word ground or the grounding symbol. The grounding electrode conductor plays a vital role in ensuring electrical safety by providing a low impedance path for fault currents, minimizing the risk of electrical shock and equipment damage. While adhering to the requirements of the National Electrical Code and following best practices for installation and maintenance, you can ensure that the grounding electrode conductor performs its intended function effectively. It is essential to consult with a qualified electrician or electrical engineer to ensure that the grounding system is properly designed and installed in accordance with all applicable codes and regulations. Proper grounding is a critical aspect of electrical safety, and it should not be overlooked. Investing in a well-designed and installed grounding system is a wise investment that can protect people and property from the hazards of electricity. Remember to consult the latest edition of the National Electrical Code and other relevant standards for the most up-to-date requirements and recommendations for grounding electrode conductor installations. The NEC is updated every 3 years, so it's important to stay informed of any changes or revisions that may affect your work. In addition to the NEC, other resources such as IEEE Standard 142-2023 and manufacturer's instructions can provide valuable guidance on grounding electrode conductor installations. Always follow the manufacturer's instructions when installing electrical equipment and components. Continuous learning and professional development are essential for electricians and electrical engineers to stay current with the latest technologies and best practices in the field of electrical safety. Consider attending workshops, seminars, and training courses to enhance your knowledge and skills in grounding and bonding. A well-grounded electrical system is a safe electrical system. Take the time to learn about grounding electrode conductors and other aspects of grounding and bonding, and you'll be well equipped to protect yourself and others from the hazards of electricity.